All right, so these notes are applications, which I know we all love so much. Don't be afraid. It's not word problems, ladies and gentlemen. They're applications. How do I apply exponential and logarithmic processes, solving to actual real life situations? So the first one we're going to look at is exponential growth and decay. And so this can be found on page 327 in your textbook. If you need extra practice problems, that's where you're going to find it at, okay? So we're going to be using this equation. It's written as a sub f equals a sub I times e to the kt power, k times t. So a sub f is your final, okay, or yeah, no, that's it. What? It's your final amount. Okay, so a sub f. A sub I, that's the one I was looking at that I giggled at myself, is the initial or the original amount. Okay, you'll see both. E is that, yes. It is the number 2.7128 blah, blah, blah. K is a constant. Okay, why is it K? I don't know, but I'm going to tell you right now, K cannot be 0. It is a constant value, depending on whether it's growth or decay. Now, if K is greater than 0, that means that it is increasing, which means we're looking at growth. Okay, if your constant is greater than 0, 1, 2, 3, 4, a million. If K is less than 0, then it's decreasing. We're looking at decay. So if K is negative, that means it is decay, not growth. All right, so let's take a look. Let's see what we do. For example, number 1, we'll say, it tells us right away it's exponential growth. In the examples that you're going to practice with in the textbook, it's not going to say that. Okay, but it says an unknown bacteria is reproducing so that every 3 hours their numbers double. We're asked to determine how many we will have in 2 weeks if we start off with 100 bacterium. Okay, well, the one thing I notice is we are doubling every 3 hours, and we want to know how many we have in 2 weeks. What I don't have is K. So the first thing I need to do is find K, find what my constant is. Okay, well, it's telling me my numbers double every 3 hours. So I'm going to use the first sentence, always. Don't try to jump around. Don't try to mix up the information. They give it to you in a specific order for a reason. So I'm going to say, well, shoot, I don't know what I start with. Let's call it 1. Yeah, and it's going to double. So my final would be 2 if my initial is 1. And then times e to the k we don't know, but we know that it doubles every 3 hours. Okay, so I can rewrite this as e to the 3k power is equal to 2. Man, that exponent. Yep, it's got my variable. So the only option I have is to take the log, or rewrite it, in log form. So I'm going to say the log base e of 2 is equal to 3k. Okay, this is interchanging between logarithms and exponential functions. And then k is going to be equal to the, remember, log base e is natural log. So natural log of 2 divided by 3, which, if we were to approximate, and on my notes, I didn't approximate out as far as I would like. So I'm going to grab my calculator real fast and say that the natural log of 2 divided by 3. Okay, I'm going to round out to 5 decimal places. Your answer is way more accurate. I want you guys to get into the habit of that with this. So it's approximately 0.23105. Sweet. Okay, so the first sentence has been used. Okay, so then it's being asked, determine how many we'll have. So how many is a sub f? How many we're going to have in 2 weeks? Maybe you noticed, maybe you didn't. Originally, it's given in hours. So for 2 weeks, we're going to have to figure that out first. Okay, we're going to have to convert. Here we go, because our time has to be consistent. Otherwise, our answer won't have any validity at all. So 2 weeks. Well, we've got 24 hours in 1 day, right? Okay, we've got 7 days in 1 week. And we want to know how many are in 2 weeks. So these are going to cancel out, and we're going to find that this is, if I move it, this is going to give us 336 hours. Now, however you convert it is up to you. I don't care. But that's what works for me is I lay it out in that fashion. Okay, so we're looking for a sub f. What is our final amount? When we start out with 100, okay, times e, raised to the, our k that we found is going to be 0.23105 times 336. Okay, so if we put this into your calculator, it gets a wicked large number. It's approximately 5.19 times 10 to the 35th power. Okay, that's so many, but think about it. It doubles every hour, and it's in 2 weeks, so that makes sense. Absolutely. You can write it out in standard notation, but I am totally okay like this. And it's bacteria, so we will say bacteria to answer it. Now, if you're wondering why we converted the weeks to hours, that's because our constant was figured out using hours. Okay, you always want to go for the time frame that's based off whatever your K is found in. Okay, so DK, it tells you the radioactive compound has a half-life of 15 years. Now we're starting off with 150. How much is remaining in 35? Well, again, we don't have K. We're going to have to find K. Okay, so half-life of 15 years. Okay, I don't know what I'm starting with. Let's say I start with 1, right? That means in 15 years, I'm left with a half. Initial is 1, final is a half, times e to the 15k power. Okay, again, I'm going to have to put it into log form. So log base e of 1/2 is equal to 15k. Log base e is natural log, so k is going to be the natural log of 15 divided by what? No, Patterson. The natural log of 0.5 divided by 15. Okay, so, and again, I didn't round out as much as I should have. So we're going to get that k is approximately negative 0.04621. Round out to 5 decimal places to keep it as accurate as possible. Okay, so now we found k, we can figure out what it's asking. How much will be remaining in 35 years? So we're looking for a sub f. We started with 150 grams times e to the negative 0.04621 times, oh no, not 15, times 35, because it's 35 years. What's remaining in 35 years, okay? So if we were to work this out, you get approximately 29 point, we'll just do 76 grams. It doesn't say how to round out for the answer, so we'll just go to the, pardon me, hundreds. Okay, sweet. All right, ladies and gents, that is exponential growth and decay. The next one that we're going to look at is continuously compounded interest and compounded interest straight out. Now, you should have seen this in Algebra 2, who knows, but this is from page 318 in your text. There's 2 different ones. Okay, the first one that you're going to see is PERT, A equals P times e to the RT power. The next one is A equals P times R plus 1 divided by N, quantity raised to the NT power. And there's big differences. One says continuously and one just says compounded. This might be monthly, daily, weekly, hourly, whatever. Big differences, okay, big buzzwords. So for the first one, if I didn't know it was compounded continuously, it says in the written continuously compounded. So right then and there, I know I'm going to use A is equal to P times E to the RT power. Okay, so we know she puts $700 into the bank. Oh, we should figure this out first. Sorry, guys. Okay, so A is the final. P is the principal or the initial investment. E, again, is 2.71828, blah, blah, blah. R is the rate, and you have to put it in decimal. It'll be given to you as a percentage, most likely. And then T is time. Now, everything for the compounded interest stays the same, except N. N is the frequency that it's compounded. So if it's monthly, N is 12. If it's daily, N is 365, because we're assuming it's in years. Okay, so make sure that you go based off of years. So back to our example. So she, whoever she might be, is investing $700. Good for her. Times E in a rate of 5%. So that's 0.05. How long will it take for her to have 1,200? So that's the final amount. How long is what we're looking for. That is your time, and it's always in years unless otherwise specified. Okay, so we're going to divide both sides by 700. We're trying to isolate the term with the variable that we're solving for. So we have 12/7 is equal to e to the 0.05t power. Again, we're trying to solve for that exponent. So I'm going to take the log base e of 12/7 is equal to 0.05t. T is going to be log base e is natural log. So we have the natural log of 12/7 divided by 0.05, which is about 10.8. So we're going to say it will take her about 10.8 years to get her desired $1,200. Okay, again, continuously. There it is. Okay, so if it's not compounded continuously, and it says here, compounded quarterly, big red flag that we are now using A equals P times the quantity 1 plus R over N raised to the NT power. Okay, quarterly, that means N will be 4, because there are 4 quarters in a month. Year. Hello, 4 quarters in a year. Okay, so how much will be in the account? That means we're looking for A. If $800 is invested, okay, so that's our principal amount, our initial amount, for 3 years at 6.5%. Okay, so 1 plus 6.5% is the rate, so it needs to be in decimal form, compounded quarterly, and it says 3 years, so it's raised to the 4 times 3 power. All right, so that means we've got 800 times 1.01625 raised to the 12th power. Pardon me. On my calculator, I'm not rounding until the very end. So we're going to say that we have about $970.73. Do not round until the very end and round appropriately, which for us here is to the hundredths. Okay, round appropriately when possible, and don't round until the very end. Until the very end. I can't say that enough, until the very end. All right, our last type of problem that we're going to see is Newton's law of cooling, and some of you might have experienced this already depending on if you've taken physics or not. And this can be found in page 331 on your textbook. Yay! I've done green and blue. Let's go orange. Yeah. Okay. Tickle in my throat. So the temperature U of T, okay, so that's your final temperature when T is time, of a heated object at a given time T can be modeled by the following function. So this bad boy, where's my highlighter? Where'd it go? I know, get it together, Patterson. Never, you can't make me. Wait for it. I know at this point you guys are wishing you could fast forward. Ha ha ha. Okay. U of T equals T, where T is the constant temperature. We'll just go back to blue. Constant temperature of the surrounding medium. U naught, okay, this bad boy, is the initial temperature of the heated object. And K is, again, a constant. But for cooling, it's our negative constant because we're at a temperature we're cooling, so the constant is decreasing. Okay, so the example we have here, and yes, you guys, the formulas will be given to you on the quiz. Okay, so be comfortable with them, understand what all of the variables stand for, how to use them, and so forth. But I will give you all of the equations. Okay, here we go. An object is heated to 100 degrees Celsius and is then allowed to cool in a room whose air temperature is 30. If the temperature of the object is 80 after 5 minutes, when will its temperature be 50? Fascinating. Oh, good. We don't know K. Okay, so first thing we have to do is we have to find K. And that's always going to come from the original info. Okay, so we have U of T is equal to, we know that 30 is T, the constant temperature, because it says air temperature. So 30 plus our equation, U naught is the initial temperature, so the object is 100 degrees, minus T times E, so sorry guys, to the KT power. Well, shoot, that's the only information we know from the beginning. Okay, well, it says if the temperature of the object is 80 after 5 minutes, so that means the temperature is 80. After the initial, we can go ahead and subtract. I don't need parentheses. After 5 minutes, when will its temperature be 50? Aha, so now we can go ahead and solve for K. Okay, so we knew that the object was at 100. The room was at 30. It cooled to 80 after 5 minutes. Okay, so that's how we were able to build the first equation. So then I'm going to subtract 30 to both sides. 50 is equal to 70 times e to the 5k power. Divide both sides by 70. So we get 5 over 7 is equal to e to the 5k power. And then, again, I'm solving for the exponent. So I'm going to have to take the log. So log base e of 5 over 7 is equal to 5k. Log base e is natural log, so k is going to be the natural log of the ratio 5 over 7 divided by 5. So k is approximately, and again, I didn't round out far enough. So natural log of 5 divided by 7, this is what happens when you try to do it at a time. Blah. Okay, negative 0.06729. Excellent. Okay, so then it says, well, when? So this is the big kicker. When? I'm looking for time. When will its temperature be 50? Okay, so if we know K, when is it going to be 50? Right? The room is at 30. I started at 100. And I want to know, when is it going to be 50? I know that K now is negative 0.06729. Okay, so I'm going to subtract 30 to both sides. So we get 20 is equal to 70 times e to the negative 0.06729 times t power, divide by 70. So we get 2/7 is equal to e to the negative 0.06729 t power. Yep, we're going to have to take the log. So we have log base e of the ratio 2/7 is equal to negative 0.06729 t. And then t is going to equal to, again, log base e is natural log. So we have the natural log of 2 over 7 divided by negative 0.06729. So we get approximately 18.62. So we're going to say that about 18.6 minutes is when this object is going to be 50 degrees. Woo! Nice job. Okay, so below you've got practice problems. Good luck. Remember, usually you're having to find K first.